Hello, welcome to the Magna Utah Earthquake Reconnaissance Briefing webinar. I'm Maggie Ortiz-Milan, and I'm a program manager at the Earthquake Engineering Research Institute.
Okay. Good.
Okay, sorry about that. To start, I'd like to quickly go over a few logistics. You can choose to listen to the webinar through your computer or your phone in the control panel. There will be time for questions at the end of the webinar. During the presentations, please submit your questions or comments in the question panel. The recording from today's webinar will be posted to EERI's YouTube channel, and presentation slides will be posted on the Learning from Earthquakes website. For those who may not be familiar, I want to say a few words about EERI. The Earthquake Engineering Research Institute is the leading nonprofit membership organization connecting those dedicated to reducing earthquake risk. EERI has been bringing people and disciplines together since 1948. By joining EERI, you become a member of our global network of multidisciplinary professionals dedicated to reducing earthquake risk. EERI achieves its mission by engaging members in institute programs. Learning from Earthquakes is EERI's flagship program and aims to accelerate and increase learning from earthquake-induced disasters that affect the natural, built, social, and political environments worldwide. The LFE website contains information from over 300 earthquakes in 50 countries. This webinar is organized as part of the Learning from Earthquakes program. Now I'd like to introduce Barry Welliver, who will be moderating today's webinar. Barry is the owner and principal engineer of BHW Engineers based in Draper, Utah. He has held many leadership roles within EERI and the Structural Engineers Association of Utah. He is currently on the EERI Board of Directors and served as the chair of the Utah Seismic Safety Commission from 2002 to 2006. Barry?
Thank you, Maggie. Well, a little over 4 weeks ago, Utah experienced its first designer earthquake along the Wasatch Front. Most people in Utah have never experienced an earthquake, and the aftershock in the following weeks and months was a good reminder that we do live in earthquake country. Today's LFE webinar will provide a broad overview of that magnitude 5.7 March 18th, 2020 Magna earthquake. We'll start with an overview of the event, including the earthquake sources, ground motion, and observed ground failures, and then move into the post-earthquake building inspection and structural impacts area, and conclude with a preview of FEMA-sponsored project titled the Wasatch URM Risk Reduction Strategy. 1 second, sorry. Our first presenter will be Keith Koper, who is a professor of geophysics and director of the Seismological Observatory at the University of Utah. He serves as a member of the U.S. Air Force Seismic Review Panel, as vice chair of the Utah Seismic Safety Commission, and is a member of the Science Advisory Board of Ethos. Keith, welcome.
Hi, Barry, thanks. Should I go ahead and get started?
You should be given permission here soon.
Okay. Okay, can everybody see my screen?
Everything is good.
Okay, yeah, thanks a lot, Barry, and thanks everybody for tuning in. And what I'm going to do is just give sort of a brief overview of some of the initial seismic observations and the initial analysis that we've done on this sequence. Okay, so the main shock happened, it was a magnitude 5.7 earthquake, and it happened on March 18, and locally it was a Wednesday morning in Utah, and this was a very significant earthquake. It was the largest earthquake since 1992 in Utah, and you can just see on the left there, there's a lot of what we call the felt reports, so something like 40,000 people reported in that they had shaking. So it was felt all over northern Utah, southern Idaho, and even in Colorado and Wyoming and so on. And on the right is just sort of our estimate or projection of how strong the shaking was. And when you see the warmer colors, you can see that the accelerations are getting up to a significant fraction of G throughout the Salt Lake Valley there. So just to echo what Barry said in the introduction, this was a very significant earthquake for those of us living in this area. And this is just a snapshot of what some of the waves look like. This is not the main event. This is just a couple of aftershocks that were coming through. And this is sort of from our Earthquake Information Center that's on the campus of the University of Utah. And on the right, I just have a listing of all the folks that that work in our group at the observatory. And so the results and the material that I'm going to show today is a reflection of the work of many different people that went into this and responded to this. And here's I just have a couple slides that show some of the damage from this event. And luckily there were no serious injuries, no fatalities. I think a couple of the later speakers are going to say more. So I'm going to go kind of quickly through the damage, but it's mainly the unreinforced masonry, older brick buildings that failed. You can see a couple of these mobile homes that were seriously damaged during the shaking. And it was a major earthquake for us, but it wasn't necessarily surprising or unexpected. And that's because there is this history of magnitude 5 and magnitude 6 earthquakes that have happened sort of throughout the state of Utah. And this is just kind of a historical picture that gives you an idea. Maybe about once every 10 to 15 years, we get a magnitude 5 or bigger earthquake somewhere, within the state. We also have evidence from basically paleoseismology that there's been magnitude 7 earthquakes that have happened here in the recent geologic past. So if you sort of do the trenching, you can kind of observe and characterize these paleoquakes. And what we think is there's been about 24 of these large, maybe magnitude 7 earthquakes that have happened sort of along the Wasatch Fault in the last 6,500 years. So on average, maybe once every 300 years, we expect to have one of these sort of magnitude 7 events. So we haven't had one yet, sort of in the historical era, but it's inevitable that one will happen at some point. This is a map of seismic hazard just for the whole, for the U.S. And I put this up there just to emphasize that the hazard in Utah, the red colors, is just as high as the hazard in other places, for instance, on the West Coast, in California and Alaska, and so on. So it is a relatively narrow region, but because of this history of seismicity and the history of big earthquakes, you can see that we do have, pretty high hazard in this area. And one of the things that makes it even worse is that most of the population, most of the infrastructure, really in the state is along this Wasatch Front, this kind of urban corridor. And so if you combine the population and the infrastructure with the seismic hazard, what you get is very high seismic risk. And so this is just from FEMA. These are based on different hazard simulations, and you can just see that the state of Utah is ranked anywhere between 5 and 10 in the country in terms of these metrics for seismic risk. So it's not really a good situation. And this is what our seismic network looked like the day the main event happened. And so we have over 200 different seismograph stations that are out. There's a variety of different sensors that we use. All the data are digitized at 100 hertz, and they're sent sort of with a latency of maybe 2 to 3 seconds to the data center, which is on campus at the University of Utah. And so this is sort of a real-time operation. were pretty data rich. We were prepared network-wise to record an event like this. But because we are seismologists, we always want more data and we want more seismometers. And so after the event happened, the main shock, within the next week, we went out and we installed or modified 7 new telemetered stations that we could use to help us detect and locate the aftershocks. And this is just what one of the sites looks like. You know, we tend to bury the instruments for thermal insulation. And so the engineers and the staff responded really well in quickly getting out there, getting the permissions during this pandemic was not necessarily easy. And we were able to fill a few little gaps that we had. And we also went out with some of the wireless geophones. And so these, we put out about 200 of these throughout the valley, again, within about the first week. And we haven't fully analyzed these data yet because you have to go out and pick up the geophone and bring it back to get the data. So it's not telemetered, but it is very valuable information. And this is, I'll show you some results now and some observations that we made. The maximum shaking, so the peak ground acceleration, and this would be horizontal ground acceleration, was a little bit more than half a G. And that was at our nearest station, LKC, which is there in the center of the figure. And you can see sort of throughout the valley, we had pretty strong shaking, above 10% G. You can also see the basin effect. If you go east towards the mountains, you get into rocks and harder, stiffer soil, so you have less shaking. But if you stay sort of north-south in the valley in the weak sediment, you get enhanced shaking. And a couple of our stations, or actually many of our stations, showed what we call a basin resonance, where this sort of 1 hertz or 1 second energy can continue on for much, much longer than the source of the earthquake. And this is basically energy that's trapped in the low velocities of the sediments in the valley. Okay, and this is some modeling we've done of the main shock, basically to get the orientation of the fault plane, to figure out the size. If you look at the table on the right, you can see sort of the accuracy we have in terms of magnitudes. And so our best estimate of the magnitude is actually 5.54, a little bit lower than the 5.7. These are from different agencies, and you can see that there's some variation. The mechanism was a low angle normal fault. It had a little bit of left lateral oblique slip as well, but it was mainly a normal event. And this is modeling of the spectra of the main shock. And so in this case, what we do is Fourier transform, right? We go from the time domain to the frequency domain. We can estimate some properties of the earthquake. And, for instance, the motion across the fault on average was about 1 foot, okay? And the area of the fault that ruptured was something like 16 square kilometers. So roughly the size, the area of the city of Magna. This shows this is about the first 3 months of aftershocks that we recorded. And you can see there's one major cluster there around the main shock, and then there's a second cluster a little bit further east. And we do think that the smaller cluster of aftershocks to the east were triggered by stress changes from the main shock. This just shows some more of these moment tensors and sort of the faulting for some of the bigger aftershocks. And what we found is that a lot of the faulting was very consistent, and it was a little bit unusual because normally with normal faults, we expect steeper dips to the fault planes. And as far as we can tell, it looks like it was mostly low angle faulting. We also augmented our normal catalog with up to I think we got about another 5,000 aftershocks, and this is from a matched filtering process. And so we were able to basically expand our catalog and detect a lot of these little tiny events that we initially missed. And this is sort of my summary slide right here. And it shows our interpretation of the geometry. So this is just a model. This is one model that fits all the observations. And the idea is that we have this curved or listric Wasatch Fault that dips down underneath the valley. And we have these relatively shallow planes of seismicity to sort of delineate the fault zone. And this is my final slide. And I know there's a lot of text on here, but I guess if you want one take-home point, it's that this was basically, it was a moderate-sized earthquake. So this was not, quote, the big one. There's actually plenty of strain that's remaining on this segment of the Wasatch Fault, and it still is possible, of course, to have inevitable that at some point we'll have one of these magnitude 7 earthquakes. So the probability of the big one has not changed very much based on the sequence of events from Magna. And then just finally, I'll just point out that all of this and more, we just released our first report on this earthquake sequence. And if you go to the webpage in red, and then you just search for Magna, you can download it and read all the technical details and so forth. Thank you very much.
Thanks, Keith. I know 54% ground shaking is impressive to me as a structural engineer, that's for sure. And this idea that our scenario magnitude 7 earthquake being 90 times the magnitude of what we were experiencing is very sobering to all of us here. So up next will be Ivan Wong. He is a senior principal seismologist with Lettis Consultants International with a 45-year career focusing on earthquake hazard reduction and public outreach. Ivan has worked extensively in consulting and research in Utah and often collaborating with the Utah Geological Survey and the University of Utah. Ivan has led in the development of the first seismic hazard maps in the Salt Lake City urban area. It's all yours, Ivan.
Thanks, Barry. I'm waiting for my present. Do you see my presentation?
Yes, we do.
Got it. Okay. So thanks again. What I'm going to be talking today about is the earthquake and more information on the ground shaking, but possibly more importantly, what this earthquake means in terms of seismic hazard and seismic design in the Salt Lake Valley and the Wasatch Front. So this earthquake is, in terms of strong ground motion, is the best recorded earthquake we've ever had in the Basin and Range province, and I'd say the Western U.S. It's also the best recorded normal faulting earthquake in the Basin and Range province. We don't have very much data from normal faulting earthquakes. As Keith stated, there were 60 strong motion stations that recorded the main shock within 100 kilometers, with more than 100 stations within 200 kilometers epicentral distance. The data set provides a good test for the NGA West 2 ground motion models. As Keith said, the highest peak ground acceleration that was recorded was 0.54 G. That's on a single component at the Lee K Center. When we talk about ground motions, we usually talk about the average of 2 horizontal components. So in this case, for LKC, the geometric mean PGA was 0.43 G. And I'll be talking, when I mention PGA in the next slides, I'll be talking about the geometric mean. The areas of greatest damage can be correlated with the areas of strongest ground shaking. So for those who live in Utah, a reminder, this is a very seismically active area. In 2016, we released the working group on Utah earthquake probabilities forecast. And we can check one box for the period from 2014 to 2633. We had forecasted a 93% chance of one or more magnitude 5 earthquakes. That was probably sort of a no-brainer. But we've also forecasted a 43% chance of one or more surface rupturing earthquakes, magnitude 6.75. So it's a seismically active area. This is a slide that Keith showed, just showing the distributions of the main shock and aftershocks. This is Did You Feel It? Map from the USGS. Again, wanted to stress that it was felt widely throughout Utah as well as the adjacent states. When you hone in on the area around Salt Lake Valley, we see that the intensities were getting up to about 7 or 8, so that's very strong to severe ground shaking. This slide just shows some of the shows the stations that recorded the earthquake within a radius of 200 kilometers. The earthquake basically occurred in the heart of the University of Utah seismographic stations, their urban and regional strong motion network. So it occurred in a very densely instrumented area, so the data set's very rich. Looking at some of the near field ground shaking, again, a list of stations on the left. The rupture distances, which we've calculated from a model of the rupture area from the magnitude 5.7, a listing of the peak ground accelerations and their associated intensities. So the intensities got up to 8 at LKC, and around the epicenter, they were generally in the range of 7 to 8. I'm also showing under the category site, the site response category for that particular seismographic station. The Q01 to Q03 are basically alluvial deposits in the heart of the valley, ranging from silt and clays, which is Q01, to Q03, which are alluvial and lacustrine gravels and sands. We had a couple rock stations, DMC and NOQ, that recorded pretty high ground motions for rock sites. This is just honing in, showing the rupture plane of the earthquake. This was a model that we adopted from Jim Peshman, a rupture plane of about 5 kilometers long, 4 kilometers wide, with a dip of 35 degrees. You can see the ground motions. LKC sits over the top edge of the rupture plane with the highest recorded PGA of 0.43. Down here at Magna, where there's significant damage, particularly to older structures, we had ground motions, for instance, at this Magna station of 0.3 G. So probably in the area of greatest damage, we were looking at peak ground accelerations in excess of 0.3 up to 0.4 G. Elsewhere to the north and south, you can see the ground motions also in the range of 0.3 G. Comparing the data with one of the NGA West 2 ground motion models, I'm just showing the model from Abrahamson et al. For 2014. The 4 panels show different bins of VS30, which is the average shear wave velocity in the top 30 meters, a proxy for site category. So in this panel, for instance, I'm showing the data from about 150 meters per second to 250 meters per second. What the slide is showing that basically the NGA West ground motion models, particularly the Abrahamson et al. Model, does a pretty good job of fitting the data. So this data is consistent with the ground motion models. In the case, there are some, of course, variability, as you would expect in any earthquake. Here in the site category of VS300, we can see that the model slightly overpredicts the ground motion recordings. The red line, by the way, is the median model, and the the dashed lines are the 16th or -1 sigma and 84th +1 sigma ground motions models. The rock size VS30 of greater than 1,000 meters per second, you can see the data fits the model pretty well. That was at PGA at 1 second, which is longer period ground motions. Again, you can see the data is consistent with the Abrahamson et al. Model. So no surprises here. If we look at response spectra, which I'm showing spectral acceleration on the vertical axis and period or inversely frequency, I've just calculated by the solid black line what a magnitude 5.7 at 10 kilometers would look like based on the NGA West ground motion models. And I'm showing some of the response spectra from some of the nearby stations. You can see the shape of the spectra are fairly consistent. There are some variations. For instance, this rock site peaks out here. This alluvial site peaks out here, but the majority of the stations peak at the same place as our prediction. The amplitudes are higher, and which just could mean that we're the NGA West, there are side effects that are not being adequately captured on a site-specific basis. I'm showing the model that I stole from Keith, which shows his listric model as being the source of the Magna earthquake. So it's a low-angle fault. I'm also showing a 50-degree dipping fault, which is the commonly accepted model or dip for the Wasatch Fault. And this has some important implications. Obviously, if the fault is listric, then the distance from the fault plane up to the surface is shorter than it is for a 50-degree dipping fault. So the $64,000 question in terms of hazard and risk and design is, did the Magna earthquakes occur on the main Wasatch Fault? And if so, is the Salt Lake Valley segment a shallow dipping fault beneath Salt Lake Valley? Now, the Magna sequence occurred in a step over, which I'll show in the next slide, between the Warm Springs section and the East Bench Fault. And so, given it's in a rather unique place along the Salt Lake City segment, is the geometry of the portion of the fault that ruptured in the Magna sequence, is it representative of the Salt Lake Valley segment? Now, realize that the Magna rupture plane is less than 5% of the whole Salt Lake City segment. So could most of the fault still be moderately dipping and not listric? Now, as I said, a moderate dip of 50 degrees has been assumed for the Wasatch Fault. We do that in site-specific hazard analysis. The working group forecast is based on 50 degrees. The USGS National Seismic Hazard Maps and the building code all assume 50 degrees. It's also the dip that we assume for most basin and range faulting, most basin and range normal faults. And one of the analogs that we based this assumption is that in the Lost River fault source, which was the source of 1983 Bora Peak earthquake, it's a moderately dipping 45-degree dipping fault. So a shallower dip would result in higher than expected in ground motions, and because it's shallower dip, it could mean a larger maximum magnitude or characteristic earthquake. Here, wrapping it up, I'm just showing the effect of having a shallower dip. On the left side well, on the upper panel are peak ground accelerations, assuming two different dips. The horizontal axis is the distance from the fault, so it goes from 0 kilometers from the surface trace of the fault out to 15 kilometers. The left panels are for a deep soil site, and the right panels are for a rock site. As you can see, close in at distance of 0, 5 kilometers, the red line is a shallow dip, 35 degrees. The blue line is a 50-degree dipping fault. You can see the differences in the ground motions. This is peak ground acceleration isn't very much. It's probably on the order of less than 10%. But as you get farther out, 15 kilometers deeper in the valley, the ground motions are 20% higher if you assume a shallow dip. I want to emphasize that most of the city is within 5 kilometers of surface trace, and so the change in dip or the difference between a listric fault and moderately dipping fault is not much. If you assume a rock site, if you get out to the west side of the valley, the difference in the ground motions are significant, out to 40%. But much from the fault trace out across to the valley, there are no rock sites, not until we get to the west side. Just showing a slide from the working group, the difference in the dips of the Wasatch Fault. Because of the way the working group determined the characteristic of maximum magnitude, the difference in dip doesn't result much difference in terms of maximum magnitude. If we assume a 50-degree dipping fault, we had come up for the Salt Lake City segment of magnitude 7.1. If we assume a 30-degree dip, it's a 7.2. So not much difference in terms of impact on maximum magnitude. So to wrap up, the strong motion records are consistent with the NJ West 2 ground motion models. In general, most of the strong motion data do not exhibit any unusual characteristics, although really the analysis of this data are just beginning. The strong motion database should be a good data set for evaluating shallow side effects, particularly up in the avenues and benches in Salt Lake City, particularly at higher ground motion levels, and should also provide a good data set for basin effects in Salt Lake Valley. But I do want to stress, as Keith has stated, this is a moderate earthquake, and it's, how things will shake out basically will be different in a very large magnitude 7 earthquake along the Salt Lake City segment. A very significant seismic hazard issue is, did the Magna earthquake actually occur in the main Wasatch Fault? And if that is the case, what is its geometry at depth? I do want to say, I think the jury is still out on whether it occurred on the Wasatch Fault. It could have occurred on a secondary fault. Is the geometry that we're seeing in this Magna earthquake, is it really representative of the whole Salt Lake City segment? If it is, if a large main shock were to occur on a shallow dipping Wasatch Fault, the ground motion will be higher in the basins due to shorter sight distances, and there may be a larger maximum earthquake. Okay, thank you.
Thanks, Ivan. That was very instructive. I think the working groups here in Utah have a lot to chew on, as do the engineers, relative to the new data that we have available for this. Okay, so next up will be Emily Kleber. She is a geoscientist at the Utah Geologic Survey, specializing in earthquake geology. She investigates how earthquakes and geologic hazards have changed the surface of our geologic time scales with expertise in the application of high-resolution topographic data, which is LiDAR, to geologic hazard mapping, paleoseismology, and field geology. She was one of the very first persons out in the field, and Emily, you are on the spot. Go on.
Great, thanks Barry for the great introduction, and just making sure everyone is seeing my speaker slide and now my first slide.
Yes, we are.
Okay, great. Yeah, so thanks again, Barry, and thanks to EERI for putting this webinar together. Today, I'm really excited to talk about the geologic effects that we at the Utah Geological Survey observed from the Magna earthquake. But first, I just want to make sure everyone has the geography in their minds as we talk about some of these places that we saw these geologic effects. So we've been talking about the Salt Lake Valley, which is bordered on the east side by the Wasatch Mountains and on the west side by the Oquirrh Mountains. And the Salt Lake Valley is bisected by the Jordan River, which flows from south to north from Utah Valley into the Great Salt Lake. And the Great Salt Lake and the Jordan River are local controls on base level and groundwater fluctuations, which will be really important for the latter part of our talk. The epicenter of the earthquake occurred in the northwestern part of the Salt Lake Valley near the town of Magna, which has a population of about 20,000 people. And some of the areas I'm going to be talking about are the Goggin Drain, Saltaire, and Great Salt Lake Marina areas, as well as the Jordan River. So one area I'm actually not going to be talking about, but it's worth mentioning, are the Rio Tinto tailings piles and ponds, which are just west of the earthquake epicenter. And these are coming from the Bigham Canyon mine. Both of these areas are highlighted with the blue squares. We do know from our state dam safety engineer that there were large fluctuations in pore pressures within these well-instrumented tailings ponds, but they stabilized after the earthquakes. There's also some reports of localized cracking and liquefaction. So we've already gotten a little bit of a geologic introduction, but just to sort of reiterate, you know, the dominant geology in this area is the quaternary geology of the Lake Bonneville cycle. So at its high stand, Lake Bonneville did fill the entire Salt Lake Valley, carpeting the whole valley with sediments, sands, clays of varying thicknesses, which has a real control on how earthquake waves propagate throughout our valley. The depth of bedrock around the Magna earthquake epicenter is about 3,000 feet, and this is based on geophysical logs and structural interpretation from geologic mapping. We do have a lot of really great understanding of what the superficial geology looks like, and you can go to our website, geology.utah.gov, to take a closer look. So the superficial geology around the epicenter is primarily this quaternary superficial lacustrine, deltaic, alluvial, and marsh deposits in areas near the Great Salt Lake. So lots of sand and clay. And just to talk a little bit more about the surface expression of the faults in the Salt Lake Valley. Our local faults include the Wasatch, West Valley, Great Salt Lake, and Ochre fault zones. These are all normal faults, predominantly dipping to the west, with the exception of the West Valley fault zone, which is antithetic to the Wasatch fault and east dipping. And you can see that highlighted in the little block diagram at the bottom of the slide. And as others, you know, to kind of echo what other people have said, the Wasatch is a segmented normal fault, and it's quite complex at these segment boundaries in their surface expression. So the red lines in the figure are showing the surface expression of the fault scarps from paleo earthquakes, and these were recently mapped with LiDAR elevation data, and then paleoseismological investigations have shown that earthquakes do rupture across these boundaries, which is really important for determining our seismic hazard. And then I also just want to echo that, you know, having our geologic understanding of the extent of paleo earthquakes and having this rich data set from the Magna earthquake is just really cool, and it's going to be so critical to, you know, going forward and understanding our seismic hazard in the valley. So this animation starts off looking at the Salt Lake Valley in map view, and then we're going to zoom down below the surface to watch the earthquake sequence over the course of about 10 days. So we start off with the 5.7 main shock hypocenter, followed by shallower aftershock sequences occurring above the hypocenter. And you can see we have a very robust sequence that pops up, and then finally we can see below the airport to the east, these are the West Valley fault zone. And if you recall from Keith's presentation, he mentioned that the main shock stress changes likely triggered this aftershock. So just a nice visualization to show that, you know, this is a complex earthquake for complex set of faults that we have. In terms of our earthquake response, the UGS was active right away. Field teams were boots on the ground by 9:30 a.m. Our online clearinghouse was activated by 9:20 a.m. And again, that main shock occurred in the morning at 7 o'clock in the morning. It was quite an exciting day. I think everyone who felt that earthquake probably can echo that. So we had remote support due to COVID-19 from some of our colleagues, Steve Bowman, Ben Erickson, and Adam McKean. They were also providing information to emergency managers, public officials that needed information about the earthquake sequence that was ongoing. And then we had field teams deploy, like I said. So all of this data that we collected over the course of the earthquake response is available in our online clearinghouse. So if you go to geodata.geology.utah.gov, this is a place where you can see all of those photos, videos, and these are resources that came from us, but also from local municipalities, members of the public. And this is still an active clearinghouse. So if you have photos of damage or any earthquake effects, anything that might be relevant that you'd like to contribute, please go to the website and share them with us. So now I'm going to move on to talk about these effects and show some photos of what we observed in the field. So most of the effects we observed indicated ground oscillation and subsidence due to liquefaction in areas with high groundwater, as well as cracking, indicating these changing groundwater levels. So this map is showing our reconnaissance areas, field stops, and then we had a small unmanned aircraft system or a drone that we flew around to take some video and make some observations from the air. And then additionally, we did look for earthquake-induced landslides and rock falls without much luck, covering the northern Ochres as well as the Wasatch Front and historically active landslides. So again, the Jordan River bisects the Salt Lake Valley, and it's this local controlled base level. So it's one of the first places that we went on the day of the earthquake. Shown in the photo on the left is evidence for some minor slumping from lateral spreading along the Jordan River. There's also extensive cracking along the banks in this area as well. The photo on the right is showing some small pools of water emanating from cracks near the Goggin Drain, which is north of the epicenter. Note that the pool edges are not completely filled, indicating that there was some localized groundwater fluctuation, likely due to the earthquake. So the next spot we're going to go to is the Great Salt Air, which is on the shores of the Great Salt Lake. This is a historic building and concert venue that had a lot of liquefaction features deposited on road materials around the and this is also right next to the Interstate I-80 State Route 202 interchange. So a lot of construction material, a lot of fill that was brought in where we saw these effects. So you can see in the photo, we saw some ground cracks as well as sand boils associated with subsurface liquefaction just off the road. And then aerial reconnaissance via the drone showed liquefaction features, including these underwater sand boils, which were also seen in other retaining ponds in the interchange area. So the groundwater table at this location is likely extremely high due to the retaining ponds and proximity to the Great Salt Lake. So we think these liquefied layers were pretty near the surface. Close to the Great Salt Lake shoreline at the Saltair, we also saw sand collapse features, again indicating this fluctuating local groundwater level just right at the shore of the Great Salt Lake, but also now in more of a natural environment. So finally, we'll move over to the Great Salt Lake Marina and focus on the road, which is highlighted in this box in teal. And then, as you can see from this aerial photo of drone-based photo, this road has already seen plenty of repair from cracking, but the earthquake definitely caused some new cracking to form, which are being indicated by the arrows. And there's a crack in the upper left that is about a 20-foot crack, and then we measured continuous cracks within the road up to 55 feet. So not necessarily your run-of-the-mill sort of road settling damage. Here's some close-up photos of those cracks. The one on the left is showing that area that was just off of the road. And then the one on the right is showing the connection between the road shoulder and the main road. Yeah. And then finally, also at the Saltaire, we did see evidence of these subaqueous sand boils, which you could see in this photo indicated by the sort of lighter buff areas within this sort of microbial mat area that is a great place for bird watching if you're in the area. And finally, I just want to do some comparison to some of the hazard mapping for liquefaction that we have in the area. So this is probably one of the most widely distributed liquefaction potential maps for the Salt Lake Valley, done in 1994 by Anderson and others. So this map is showing the soil susceptibility information with the seismicity of the area in order to describe the likelihood or potential of liquefaction for probabilistic scenario events. So this liquefaction, the categories are based on the probability that ground accelerations due to earthquakes will cause liquefaction within the next 100 years. And this is the coarse map, but given our observations in the field, this map indicates and matches the places where we saw liquefaction. So the UGS Hazards Program has a geologic hazards mapping initiative underway where we're mapping urban quads in Utah for a suite of geologic hazards, including liquefaction. This mapping is based on geologic information from a dense array of geotechnical reports that we collect from local cities and municipalities, as well as geologic, just the run-of-the-mill geologic maps, excuse me. So maps of this resolution are really necessary for making informed planning and building decisions in urban areas. And we have a newly released Utah Geologic Hazards portal, which you can find on our website. And this is a great way for you to explore what data are available in the area. So based on this mapping, this quad indicates areas where we saw evidence of surface groundwater fluctuations just east of the tailings pile. And I finally just want to touch on some work by Steve Bartlett at the University of Utah in the Department of Civil Engineering. This is USGS funded work to show the liquefaction displacement for a specific magnitude 7.0 scenario earthquake. Since it's not quite the same as, this would be that large magnitude earthquake we've been talking about. So this work I just wanted to show because it is in review at the UGS and will become a miscellaneous publication. So have a look out for that. And with that, I want to thank everyone at the UGS who's been involved and thank everyone for listening.
Thanks, Emily. That was great. I feel like this was a great test for us all, field test, I should say, for the big one that we all need to be prepared for. So thanks. So we'll stay on the surface of the Magna earthquake and talk a little bit about the post-earthquake response and some of the structural impacts. Trent and Crystal were presented with some big challenges in creating and managing the post-earthquake inspection program in Magna. And as I said to them, there's nothing like being in charge of something you've never been in charge of before. So Trent Sorenson is the chief building official for the Greater Salt Lake Municipal Services District and serves many metro townships in unincorporated communities. Prior to his work with the district, he spent 10 years working in the building department at Salt Lake County and 11 years working in building construction in southern Utah. Crystal Halbert has been a city engineer for Magna Metro Township since 2018. She began her career in heavy civil construction management, and then went on to structural design for commercial buildings and finally to civil design for residential homes. She has spent the last 4 years in municipal engineering. Crystal received her Bachelor of Science in 2006 in civil engineering. So Trent and Crystal, walk us through the challenges you had setting up the post-earthquake hazard investigations.
All right, thank you, Barry. Can you see our screen?
Yes, we can.
Right.
Just advance it so we don't see your faces.
Okay, perfect. So just to start off, Trent and my presentation isn't as technical as a lot of these presentations have been. It's more just the perspective of a local building official and a city engineer on the logistics of doing inspection after an earthquake. We'll talk about what we learned after being thrust into this situation. And like Barry said, we had never inspected after an earthquake before, and how we adapted in general, how we adapted with COVID-19. That kind of threw some curveballs, and what we would do differently.
And so kind of like right that day one, right after the event, me being the building official, it was kind of like, you know, what are we going to do now? Where do I start? What's my role? You know, it was a little overwhelming, a little chaotic. The fire and police had already evacuated about 5 blocks of the older buildings facing Magna, Maine. And the people that were evacuated were looking to us to be able to reoccupy the buildings. Most of those buildings were commercial buildings, but there were a couple of small and older apartment buildings. And everyone was looking at me to get clearance, you know, the owners, the tenants, city officials, the Red Cross, all wanting to know if these people could get back into their apartments. But the condition of some of those buildings was in question, where they were old unreinforced masonry buildings. And a couple of the owners of those buildings actually came to me with pictures, you know, even on day one with pictures, historical pictures of their building that they brought to me in an effort to prove that the cracks and some of the displacement and different things that I was seeing on the buildings were pre-existing, and that, you know, trying to get me to, I guess, ignore what I was seeing so that they could reoccupy the building. So there was a lot of pressure of just trying to accurately evaluate what was going on. In addition to that, there was people, owners, news, the news media, public officials, and just curious people in general vying for our attention, interrupting us and trying to see, you know, what was going on. And so we realized quickly that we needed to get a little more people involved and needed help, and we needed to get better organized, you know, after that first day. So we reached out to the engineering department of the county that we have a close relationship with to get assistance.
So starting right after the earthquake, I was doing inspections on government facilities, rec centers, libraries, prisons. And then the next day I got a call to go and look at Magna, Maine. I was Magna's city engineer and the surrounding area. So like Trent said, we gathered up all the engineers in our division as well as planning's inspectors to go out and to the most vulnerable areas and do rapid inspections. Some of the staff had ATC 20 training and some didn't, and that's a huge lessons learned as far as it's good to have everybody who might be involved in these situations get that training beforehand. We enlisted the help of Barry, and he came out to do kind of a crash course on ATC 20 training for all the staff. And then we went and looked at a few buildings together to make sure everybody was on the same page, that they saw what, you know, issues possibly could be, and that they would kind of record them the same way that we would want them to. And then we split everybody up in groups and had them go down not only Magna, Maine, but some of the streets near it where the older homes are located in the areas that we had the most concern about. And we had them go until we started not seeing, you know, any more concerns. The main issues that we found were, you know, it was mostly damage to chimneys and detached garages, but there were some homes that did have some substantial damage. And about twice a day we'd get together, and this only went on for a couple days. About twice a day we'd get together and discuss what damage we'd seen and make sure as a group we were all on the same page and looking for the main issues.
And so after that, as we kind of assessed in the field what was going on, we realized that we couldn't go and see every street in our jurisdiction, nor did we think it was a good use of our resources to go and look at every street based on the damage we were seeing. And then all of a sudden we started getting phone calls. You know, that first day we probably didn't get a lot of phone calls, but after that we started to get a lot of phone calls from owners, tenants, building owners, commercial, residential, calling us to try and come and look at their building to see what kind of damage they were. And we quickly realized that with the volume of calls coming in, we couldn't just run out every time somebody called in. We couldn't run out and view those buildings. And so we needed to address that. And then having the COVID-19 on top of that, it was a concern for us because unfortunately, most of the homes and buildings that did have damage were older, unreinforced masonry buildings. And many of those buildings are and were occupied by the more vulnerable population for COVID-19. They were elderly, underprivileged, people with other health complications. And so we did not want to unnecessarily expose the public or our staff to COVID-19 if it wasn't necessary. And so to come up with another solution. Our GIS team, and kudos to them because they jumped on this within a matter of days and created an online survey where the public could go in and put their name, their contact information, and they could put the kind of damage they were seeing in their home, add comments, add photos and different things like that. And they could fill that out and submit it to us. We then, and the idea, we promoted this online via the media, our websites, and then we had our internal staff direct people when they called in to this survey. And the idea was that we could use this information to hopefully triage the reported damage and see what sites we actually needed to go to. With that data, our GIS people also created some of these maps and dashboards and these were based on the calls coming in and the types of damages, and we had different maps depending on what kind of categories they hit, and we could kind of see some of those hot spots and things that were going on in real time as that information was coming in. And from there, Crystal's going to talk a little bit about what we did then with that information.
So like Trent said, the GIS team really got on top of it to make this survey. And initially they were going to put in kind of moderate damage, severe damage. And so in the midst of looking at everything, and everything went really kind of quick in this time frame, I called them up and said, you know, don't put moderate and severe. Let's get some different parameters. And so that went out, and they did click on some different things if there was certain kinds of cracks and as they filled out the survey. But as we started getting that survey in, we realized it didn't really triage and kind of group them into categories for us to know. And we had hundreds of them. And so and we couldn't visit, you know, hundreds of these. We didn't have the manpower at the time. So we set up kind of a calling tree. And myself and one of the staff who has some structural experience, we came up with a list questionnaire that some non-technical staff that we had could call and start calling through these hundreds of surveys that we're getting and categorize them based on specific questions that we had them ask. And here, this slide, you can see it. I just did kind of what we called category 4. We had different categories that they ended up getting placed into, and category 4 was kind of one of the ones where we thought we're probably going to need to go do a site visit. So the first round of calls was done by non-technical staff, and they took it from 400 something down to about 100 came in as things that we might need to go do a site visit. We then had a second round of calls done by engineering staff to try to see these questions and see what actually really happened. And they looked at pictures and talked to the residents a little bit more. And it was kind of a difficult process, and we definitely, I feel like it might have been easier for us to go into some of these homes than to talk to the residents, because sometimes residents are very concerned, so they kind of make things sound a little more intense than they actually are, that there's more damage than there is. And sometimes residents don't seem to think that damage that has happened is as severe as it is. And so you had to kind of look past the way the person was reacting on the phone and try to look at the pictures and talk to them a little bit. From there, we pared down that we were really only concerned of about 20 that we wanted to go and actually do a field inspection during COVID-19. I mean, this was right in the heart of kind of the shutdown. And so we put on masks and gloves and went and did about 20 of them. Some of those homes were not really a big deal. And then there was some that we definitely put a placard on and kind of talked to them about that. We always made sure, both when the non-technical staff was calling, when the engineers were calling, or when we were visiting, to communicate to the residents that we weren't, we're doing a rapid inspection. We were not doing a full evaluation. And if they were concerned, and when we let people know that we wouldn't be visiting them based on their answers, that if they were still concerned as a property owner, they could go out and hire an engineer to look at their building more. But that due to the volume and everything, we were trying to find the most severe cases. So we let them know that they were always welcome to, get an engineer to look at their building.
And so some of the challenges that we did, I was going to talk just a little bit more about some of the challenges that we had with the earthquake in general. And these are some of the pictures of some of the things we had. But we had people, it was unique dealing with people, because some people we had not wanting us to look at their buildings, even if there was damage. Literally, some of them chasing us away out of the street or yelling at us or trying to get us away from their homes because they were afraid of government in general, government involvement. They knew they didn't have money to make repairs, or they were afraid that we were going to, kick them out of their homes and not let them live there anymore. And so there was some part of the population that was just afraid and didn't want us anywhere near them and wouldn't report that damage. And in contrast, there was the other side of the spectrum where there were people with really, it didn't appear that they really had any earthquake damage, but they were touting that they did and trying to get us to come out there and declare that they did and those kind of things. And my guess is that they were trying to, get some non-earthquake damage things repaired, or they thought there was going to be money involved that we were handing out and things like that. And so trying to deal with both sides of that coin was a little bit complicated. And the other complication we had is that day 1 and 2, people were somewhat, they understood that we were dealing with an earthquake and that we were busy. We couldn't do our normal functions. But soon after that, developers, builders, homeowners that were doing remodeling projects, people expected us to be able to do our normal inspections and our normal plan reviews and our normal processes, especially with COVID-19 and trying to keep the economy running. So we tried to, it was a challenge to make sure that we were trying to deal with the earthquake response, but at the same time, still be able to accommodate inspections and keep that work going forward. And speaking of kind of that, understanding the challenges with the earthquake and COVID-19 compounding that, some of the things we did is we kind of put our top priority on reviewing engineering reports for buildings and permits that were earthquake related. So if those reports came in, they went to the top of the list and we jumped on those to try and get those turned around as quick as possible. We were also very careful not to displace people, with the exception of that initial apartment building on Magna, Maine. No one was kicked out of residential buildings in our jurisdiction. We were very careful to kind of not be too overly cautious on damage to buildings to understand that a lot of these people didn't have somewhere else to go if it was still safe. We were also trying to be very careful when dealing with people's buildings. These are their personal property and stuff like that. Just one quick story that happened on day 1, just dealing with different people and whatnot, is one of the emergency personnel on scene on day 1 requested a track hoe to come in and knock down one of the commercial buildings on Magna, Maine, because he felt it was dangerous based on his experience with fires and different things. And luckily at the time there was an engineer out there on site kind of helping us, and he looked at the building and said, you know what, I think it can be repaired. I don't really think it's that dangerous. And we were able to call off that track hoe from coming and avoid that building to be torn down. And once they did get engineers into that building, the damage was fairly minor and they were able to repair it fairly easily. And so I just caution, it was we had to be very careful on dealing with other people's buildings, on telling them what they could and couldn't do on those kind of things. Just some of the challenges that we had.
Right. One other thing that we realized was really important was communication. We realized that there was going to be people who were really frustrated with us as far as putting the placards on the front of their businesses and changing the occupation. People would call elected officials being frustrated, and the misinformation can spread very quickly. One of the things we had to make sure that we focused on was just life safety, and keep that at the forefront of doing our job and being ethical with regardless of the kind of the backlash of if we thought a building was unsafe, to move forward in that direction. And one of the things we found very useful was to make sure to communicate as quickly as possible and as much as possible to elected officials and to the public of what the process, the ATC 20 process is, and what we're doing and what's happening. And so Trent and I went to the first Magna council meeting that they had an emergency one, and we went there and discussed with them what the process was, that we were doing rapid inspections and how everything worked. And that helped a lot. We also did some press releases trying to let the public know to look at their chimneys and what we were doing as far as inspections, and that they could get an engineer themselves, a private engineer, to look at things. And we also posted that information on city websites. And then we also tried to talk directly to frustrated residents. Some people it helped, some people, you know, it didn't. They still were frustrated, especially businesses on Magna Main, as far as the process of needing to have them do reports and things.
And so just to finish up, just on a couple other lessons learned, and I'm not going to go over every one of these, but some of the big things that I thought about and things that we're still dealing with is to make sure, kind of like Crystal said, we need to make sure our staff is up to date on the process, and not just the inspectors, but all the staff, your engineers, anybody that you're going to have to enlist the help of that day. Also keep staff, and I didn't write this down, but keep staff informed of what's going on, the communication not only going out to the public, but internally. I learned that, you know, my permit techs and other people in the office were answering phones, and they need to know what's going on because they're the ones communicating directly with the public. And just, you know, I put down here, don't overpromise. I think on that day one, I kind of got caught off guard where people would call me and I'd say, well, I'll be right there. And within an hour, I realized, oh, I can't be right there. So not overpromising and not giving people the kind of that false sense of what our role is, that we're not coming in and we're not fixing things and we're not handing out money. We're here to kind of help assess the situation, but we're not taking on that role of some of those things that they think we are. And anyway, and the last one, I just said stop and take a breath, because it can be very overwhelming very quickly, and we just need to breathe and we'll make it through it. But that's really all I have. I appreciate being able to be here and kind of chime in and be a part of this process. Thanks, Barry.
Thanks, Crystal and Trent. My hat is off to you guys. Boy, I was watching you under fire. You were baptized under fire for sure in this earthquake. So, and you did a stellar job. Okay, next up we have Jessica Chappell. She's a structural engineer and associate of Reaveley Engineers with 16 years of experience in structural consulting. She serves on the Utah Seismic Safety Commission as the representative from the Structural Engineers Association. She has also organized the EERI Utah chapter resiliency workshops, which are wonderful events if you can tune into those at all, and represented at those events, represented Reaveley in partnership with the University of Utah and its community resilience program. So Jessica, it's all yours. Mike. For some reason, we're not hearing Jessica. Vida, Maggie, could you check on that?
Yes, I'm on it. I see that she is supposed to be heard, but we do not hear her. Maybe she muted herself on the computer or actual computer.
Well, Jessica, if you can hear us, we are having trouble hearing you. Looks like she's rebooting, maybe. So while Jessica is doing that, I'll take an opportunity to tell you a little bit about my perspective. It was an exciting event, to say the least. We were on our toes, but it was a useful event for us here in Utah. It was a tremendous learning opportunity, and as you'll see as the program develops here, we're going to capitalize on that for our unreinforced masonry buildings that we have here. It was talked about constantly by people both that were heavily affected by it and those of us who lived far away from it. It just was a matter of conversation that permeated the news media for weeks and weeks. And as I mentioned earlier, the aftershocks were definitely bringing everybody's attention back to focus that these things are real, and that all these years when we've been talking about this being a likelihood, the reality certainly hits home. Jessica, are you back with us? Not hearing her. Still can't hear you, Jessica. Should we flip to Sean real quick and see if we can get Jessica offline and work with her?
Yeah, Barry, why don't
yes,
we do
let's
that?
do that.
Okay. So Jessica, we're going to take you offline and bring up Sean, and then maybe we'll work with you and see if we can get your voice back into the slideshow here. Okay, so next up is Sean McGowan. He is the Earthquake Program Manager and Building Science Lead in FEMA Region 8. He collaborates with state and local leaders in the Rocky Mountain region to mitigate earthquake risk and adopt resilient building codes. He is a professional engineer licensed in Colorado and has worked on projects in Mexico, Peru, and Ethiopia. And as you'll see, he is very, very, very interested in our state right now because of the high profile we have for our most vulnerable building type. Sean, are you there?
Can you hear me okay?
Yes, we can. And I can see your screen for your outline.
Okay, great.
Great.
Thanks. So I figured I'd start with a quick outline of what we're going to discuss today. So first, I wanted to focus a little bit about the emergency management, earthquake response during a pandemic. As you can imagine, that's a little bit different than normal operations. And then, as it has been discussed before from the folks from Magna, unreinforced masonry or URM risk is a really big deal in Utah, not just in Magna, but throughout much of the state. And so we'll talk a little bit about why that risk is so important. Then we're going to shift to focusing on what we're going to do about that risk and how we're trying to decrease it over time. And then we'll end with a path forward. And so, for just a quick story, that when you join FEMA, you go to orientation. One of the things that happens is they give you an exercise at the end of orientation. They basically stack multiple disasters, one on top of each other, all hitting the same poor little town that just gets demolished over and over. And you sit there and you think, this couldn't possibly happen. Why on earth are they wasting our time with an exercise that's just so unrealistic? And then 2020, we realized, hey, actually, that was pretty good training. We realized that in the middle of the pandemic, we had to try to find a way to help the state respond to this disaster. And so normally what happens is that's a threshold for a certain amount of damage for it to be declared an official major disaster declaration. And what that means is that you have to add up all the damage and audit the damage you're seeing out in the field. And the state and FEMA do this together. But unfortunately, we were working remotely because of COVID, so there was no travel. And so this ended up being the first virtual assessment that we know of in FEMA history. And so you take a look at this picture on the right, and you can see what looks like maybe it's a damage. And what we realized was, actually, we couldn't actually go out and see this ourselves. Normally, engineers like to get out really close to a structure and really get a sense of the damage. But instead of this being a picture we took, it was based on a report that the State Historic Preservation Office gave us, and combined with Emily's group at the Utah Geological Survey, the State Historic Preservation Office was one of the groups that really got on the ground early and kept us all in the loop on what was going on because we couldn't get out there. And so what we're trying to figure out remotely, this is possible chimney crack due to the earthquake, or it could have been pre-existing. We're not really sure. It's an old building. And so we figured, hey, what would anybody else do? Let's look at Google Earth. But when you go to Google Earth, it's not really helping very much. And not being able to get out there, it's a 1-hour flight to Denver, from Denver to Salt Lake City. I would have been on the next plane out there this day, but we weren't allowed to travel because, rightfully so. And so this just made the whole process a lot harder for the emergency management side of things. And also something I want to point out is that not all disasters really make the news. This one, thankfully, nobody died. But there was a parapet that was damaged on a warehouse. And you can see that the parapet fell down right on the sidewalk right here. And what's interesting is this building, I looked a little closer, it's actually partially retrofit already. You can see the ties pulling the wall in against the floors and the ceilings. but the parapet wasn't braced. And 95% of the time, that sidewalk has a line of people waiting to get into a homeless shelter next door to get breakfast in the morning. But because it was a cold night and it was rainy outside, nobody was waiting there that morning. And so thankfully, because there would have been tens of people who would have lost their lives, and then we would have been making the news for sure, but I'm glad we didn't. But because this wasn't a life-threatening emergency, it ended up taking a backseat to COVID. As has been mentioned multiple times already, this was right at the heart of when COVID was really ramping up in mid-March, and we all realized just how bad it was. And so the major disaster declaration process, what helps people get federal aid, was pushed back by a couple of months, just given the complexities of multiple disasters all combined. And because like emergency rooms, emergency managers, we also have to triage. We have to worry about protecting human life first before we can worry about recovery. And it, honestly, just on a human level, it was heartbreaking to receive emails from residents asking us, hey, can you help my elderly father? His house was damaged and he doesn't have earthquake insurance. Or, you know, my homeowner's insurance isn't covering it. Or small businesses that said, hey, can you help us get back on our feet? We're already getting hammered by COVID, now this happened. We had to just tell them, no, not yet. FEMA can't do that because it's not officially declared. But now that Magna earthquake has been declared, and so I'd encourage you, if you or anybody you know was an individual that was impacted by this disaster, this is really fairly recent news. Please call the number here, and I'll copy it again at the end of the presentation so you can see it. Because people who are members, residents of Salt Lake or Davis counties are eligible for assistance from this earthquake. And one more thing, speaking of viruses, social media rumors were viral right after this earthquake. And FEMA, and apparently according to a lot of people, FEMA and the University of Utah were predicting that there'd be a magnitude 9 earthquake within 2 hours along the Wasatch Fault. Now, aside from the fact that that's physically impossible, the fault simply isn't big enough to host a magnitude 9 earthquake. What this did was it freaked people out. Whenever there's a crisis, people go into survival mode. They make a run on the bank. They get some of their savings out. They go to gas stations and fill up their tank. They argue with their neighbors. Some people were literally heading to the hills to get out of the way of this earthquake. And so what this did was it caused a panic in a lot of the area. People were wondering, where can I get the right information? They were coming to us, they're going to the USGS and the State Geological Survey, but also they were going to Twitter. And sometimes that's good and sometimes it's not. And so this took a lot of time away from the emergency management response because we had to essentially put out a fire of people freaking out over something that wasn't likely to happen. And this just really took time away from emergency management. It's just one of the things of, in addition to the COVID and the earthquake, then we had this Twitter storm blown up. And while a magnitude 9 isn't possible, as we've heard before, a magnitude 6.75 or larger is quite possible. There's a 50% chance, 1 in 50 chance over the next 50 years we'll see an earthquake like that. And Ivan did a good job covering that already. And so you don't even need a geology degree to see why. This is a picture I took in a plane on the way into Salt Lake City back in February, and you can see clear as day, that fault is right there waiting to go off. And there's brand new homes getting built right along this fault, and so people are going into harm's way. And I hate to joke about it, but we were literally talking about disaster movie level losses that would happen if this earthquake did. The number of people who would die would be more than what we saw for New Madrid in the 1800s, for Alaska and Anchorage in 1964, for San Fernando in 71, Loma Prieta in 89, and Northridge in 94, and Seattle and Nisqually in 2001. So this is a big deal. We'd expect about 2,500 people killed by this earthquake. And that seems like a shockingly high number, especially for a domestic earthquake. And the reason for that is unreinforced masonry. I know we have a lot of earthquake engineers on the call, but we have a lot of people who maybe aren't as familiar. So I just wanted to express to you how important this is. Unreinforced masonry buildings are essentially brick buildings that have little to no steel holding them together. And so there's not much preventing them from falling apart in an earthquake. Even low levels of shaking can kill people. And the impacts, the reason that the impacts are so strong is that these URM walls often collapse outwards, as we saw in Christchurch in New Zealand just a little while back. And these falling bricks are common killers in earthquakes because they can endanger pedestrians, people on buses and bikes and cars, and even undamaged buildings that are next to these brick buildings. You could be in a perfectly strong building, but if the building next to you collapses onto yours, you're in some pretty severe danger. And so to me, this makes what we think of usually as a private risk actually a public one. And these are killer buildings. And we call them that because just how deadly they are. I mean, there's a high concentration of these URMs in Salt Lake City, over 30,000 of them. and 147,000 along the 12-county Wasatch Front, the most populated part of the state, which is also, as Keith was showing us before, is right near where the Wasatch Fault is. And there's about 440,000 people at risk in these buildings, if you do the math from the census. That's equivalent to what the population of a city like Miami or Oakland or Minneapolis. So there are a lot of people in harm's way in these buildings. But it's not all bad news. Now, when you get enough emergency managers or earthquake experts in a room, eventually the conversation, it starts out like this, and then people freak out more and more, and they get all spun up, and then it sounds like this. And then a half hour in, you realize you ended up talking about the apocalypse without even knowing it. And so I just want to point out this isn't all bad news. There is a lot of hope. Engineers know how to fix the problem. We know how, just like we know how URMs fall apart, we know how to hold them together, or at least prevent them from catastrophically collapsing. Now, this won't necessarily protect the building, but in a lot of cases, it'll help the people inside escape safely. But the reason these buildings stick around is not because of engineering or a lack of scientific knowledge, it's because of economics. People love Victorians, Georgians, Tudors, brownstones. These are iconic architectural styles and people love them. In fact, I myself used to live in this URM in Denver until I got wise and we moved out. And so the solutions we need aren't simply engineering, we also need economic and policy decisions. And so how we're going to go about that is to find a way to fund all these retrofits. And you might at this point be thinking, gosh, 140,000 buildings, you can do the quick math, just realize how the heck are you going to pay for something like that? And it's a fair question, but one way we're going to support this is through the National Mitigation Investment Strategy. And for those that don't know, this is a nationwide strategy that recommends resilience and investment priorities to benefit the whole community. And so we're having support in Utah from the local and state government, as well as FEMA and other federal agencies, and even nonprofits and private sectors getting in on the act. And this is fantastic. It's been a really good, strong partnership. And through this strategy, there are three main goals. The first one is just show that mitigation reduces risk. Second, coordinate those investments. So instead of pointing all in different directions, pursuing different things at the same time, have multiple levels of government and multiple sectors all pointed in one direction to buy down the risk for one really big problem. And the third goal is make the investment standard practice. So instead of it being something that a bunch of us get on a ERI webinar and nerd out about, it's something people are talking about at the dinner table and with their friends. And Utah agreed to be the first pilot, which is fantastic because it gives us an opportunity to really test out this process, to really try to help the people of Utah. So the priorities for this process are, first, develop a risk reduction strategy. And we kicked that off back in February when we could actually travel. And we're hoping to finalize it by the fall. And the second thing is, once we have that strategy nailed down, we're getting close to a 90% draft now. Once we have that fully nailed down, we want to work on an engagement outreach campaign that targets both the public as well as key decision makers. And some example recommendations, this is still not fully baked yet, so bear with me, but some example recommendations. Right away, schools went to the top of the list. People said there are so many kids still in harm's way in schools that have not been fully retrofit, and most parents have no idea. So we need to really target schools as our #1 priority for URMs. Then the second one is for the engineers in the virtual room. I think we all know well how many potential loopholes there are in reuse and retrofit of buildings. There's so many ways people can get around the requirements. Things like 1 and 2 family buildings can get around them. You convert an apartment to a condo, but as long as you don't change the occupancy, you can kind of keep things the same way structurally. And even re-roofing, there are so many tricks people can pull with re-roofing where they don't have to retrofit. And I've seen too many of them out in the field. And so we're hoping, and this is coming from the structural engineers community in Utah, saying, you got to fix this. You got to help us close some of these loopholes because there are opportunities to fix this problem without adding much cost to other projects, and people are ignoring it. And so the way a lot of this happens is through partnerships. And the Seismic Safety Commission in Utah is one of the strongest in the country, and it's led by the Division of Emergency Management, Utah Geological Survey that Emily comes from, and Keith's University of Utah Seismograph Stations group. Those are the 3 leaders, but I'll zoom in on this graphic so you can see just how strong a multidisciplinary group like this can be. There's contingency planners, there's emergency managers, the governor's office is involved, the Department of Transportation, FEMA and the USGS are advising it. And so this is a really good, strong group that's making a lot of change in the state. And we're optimistic about this pilot for a few reasons. First, leadership at the local, state, and FEMA, both in the region and headquarters, we're all in alignment on this. It's very rare, even in one organization, to have top-down, no matter if it's private or public, for everybody be bought in on the same thing. We have that not only at FEMA, but at the local and state level as well. And even the private sector, like I mentioned, is getting involved as well. We have a strong foundation of partnerships, as you saw on that last slide. There's already a good existing foundation of groups that are working together on this issue. And ultimately what inspires us and gets us out of the bed in the morning, even in the midst of a pandemic, where we're working on this, we're at basement offices, is that lives are at stake. And it doesn't matter where we are or how we're able to work on this, we're pushing this forward because people are really in harm's way. And I end on this because this is some pictures I took during a recent trip to Utah. And you can see there's this one neighborhood where there's a lot of young families moving in because the architecture is charming, the streets are walkable, there's cool new restaurants opening up. It's like a hot spot where people want to move to. But one by one, I noticed that 8 times out of 10, I was walking by unreinforced masonry buildings. And these are going for a pretty penny, and people are flocking there because it's a popular neighborhood. But they're also death traps. And so we want to prevent that, or at least let people know what they're getting into. Whether if there's something in the real estate process or through better promotion of retrofits or even earthquake insurance, let people know what they're getting into so they can weigh the costs and benefits themselves. And at the end of the day, the last thing an emergency manager wants to hear is, why didn't somebody do something about this? You knew this was going to happen and you did nothing. We've heard that far too often in our field. And the community in Utah and at FEMA, we do not want that to happen. So we're really backing this effort as much as we can. And we're optimistic about the future, and we appreciate the partnerships. And thank you for the time.
Thanks, John. That was very good. One question for you off the top of my head is, were you an engineer before you moved into that URM in Denver, or did you get smart when you were living there?
I was a very young green engineer at the time.
Okay. We're going to circle back to Jessica and get her online to give her presentation. One thing I would like to point out as she's loading up her presentation is, because of the overrun here in terms of length of time, we won't have time for questions at the end of this, but I do encourage you to still write in questions. We will answer each and every one of those in the follow-up email to you. So if you have questions you would like the panel to address, please feel free to answer them. Jessica, are you with us now?
Okay, I'm hoping so. Can you hear me?
Yes, we can. We see your screen too.
Excellent. All right, from my basement office, we got the technology back in line. So we'll go quickly. I know we're over. As a structural engineer, this was a pretty exciting event. This was the largest earthquake that I had ever experienced, and my first significant one in my hometown. So as a structural engineer, we were receiving similar calls to what Trent and Crystal were receiving, more from the commercial end of things, from building owners and tenants. We did spend a lot of our time explaining the difference between structural damage and non-structural damage. I'm going to skip through a couple of these things, but I did want to just reiterate our large stock of unreinforced masonry buildings. We did not adopt the Uniform Building Code until the 70s, and that was the first time we had any kind of restrictions on unreinforced masonry building. So we have a very large number of those buildings. So we'll go ahead and click through the pictures. You saw this kind of now iconic photograph, I think taken by Emily and her partner out in the field the morning of the earthquake. You can see some unreinforced masonry that fell off the building and blocked the sidewalk. But a little further afield in Salt Lake, you can start to see some of this classic earthquake damage in unreinforced masonry walls. So you're seeing a pattern of X cracks that is evidence that the building has moved in the plane of the wall in both directions, right? It's as the building moves to the left-hand side and a crack opens up in that direction, and then due to the earthquake shaking, we move back the other direction and we open up another crack. So, it's interesting. This is not that close to the epicenter in Salt Lake City. We also found evidence of out-of-plane masonry wall damage. You can see here, this is a multi-wide unreinforced brick structure where we had a little blowout at the top of the wall. You can see the red lines highlight the header courses, which are bricks turned on end in an effort to tie the two or three withes together in a masonry wall. You can see that the lines that are created by those header courses, but again, they weren't strong enough to hold this wall together in the face of the shaking that was seen here. Here's another building. There were X cracks on this structure, but you can see kind of up close and personal, there's some twisting going on at the corner of the building. So again, classic URM damage in Salt Lake City. This is the photograph of a common apartment building type in Salt Lake City. We're looking at 3 stories of unreinforced masonry with a basement below. And this photo was from the Deseret News. And I should back up, a lot of these photographs came from the EERI Virtual Earthquake Reconnaissance report, as well as the UGS archive. So, and as well as some from my own office. So you can see here, we've got piles of bricks on the ground. Those appear to all be from the parapets crumbling below, but you can see in that little blurry close-up shot, there's some significant damage to that tall chimney. So looking at a more residential structure, there was a lot of chimney damage. I think you saw that in Trent and Crystal's photographs as well. You can actually see the cap for the chimney on the ground here. On the same structure, there were multiple chimneys, and you can see the damage there. So one of the significant areas, there's a community impacted. We're about 2 miles away from the epicenter. And there's a report in process right now by Bruce Mason. He's given a summary of findings, and the labeled image up here on the screen comes from his summary report showing the steel piers that have tipped over. And essentially, he's finding 48 of 206 of these modular homes that have been dislodged. Many of them fell to the ground. Luckily, there were no fires due to gas leaks or other secondary hazards. So this may be a significant event because all these homes did have straps, and they just weren't good enough, whether they were undersized or there were problems with the anchors or corrosion problems. We just don't know yet, and Bruce is working on that report now. So in the early stages after the earthquake, the Red Cross did open some evacuation shelters. Most residents impacted by that were displaced were able to relocate with family and friends, and they didn't remain open long. So another type of failure that we started to see are these connections between walls and roofs or floors. So what you're seeing here is a steel bearing plate where there would be a structural framing member sitting on top of this that's maybe obscured by the flooring or the ceiling. And so you can see as the building moved, these anchors started to pry themselves free of the wall. Luckily, of course, there's no collapse, but there's definitely some damage and some reduced capacity in these connections. So this partial collapse is due to another wall to roof problem. And essentially what happened is as the adjacent wall moved, the roof didn't have the strength to support the wall. So it appears that the wall was braced at the steel framing elements. Looks like there's a steel joist there on the left side of the page. But the roofing material between those joists just wasn't strong enough. And so we had a collapse here. Okay, so moving into non-structural damage, partition walls that was a very common damage even in new structures. You can see some tall building contents that just collapsed because they weren't braced. Here we saw some brick veneer fall off a relatively new structure. This could be due to masonry anchors that might have been undersized, or maybe a few of them were missing, and potentially there might have been a problem with the lintel support at the bottom of that brick. Again, here's a brick veneer problem. There's no movement joints detailed in this wall, so you can see the corner tried to restrain itself, and those cracks formed in the shaking. So here we have more architectural elements that are damaged and some pretty stark differences in severity. You can see a light that might not have been braced appropriately, swung down and pulled down some ceiling tiles on the left-hand side. And you can see on the right, there's masonry partition walls, unreinforced masonry partition walls on either side of this corridor. And so whether the ceiling would have collapsed without the masonry falling or not, I don't know. But ultimately, there was a pretty major failure here. And of course, it's right at the exit of this building. Here you can see some damage due to maybe joints that aren't detailed as well as they should have been. On the left-hand side, you can see the carpet buckled at a movement joint instead of having a cover that would allow that movement, potentially preventing that door from opening. On the right-hand side, you can see what looks like it might be a bearing column has a big crack in it. Ultimately, this is an unreinforced masonry partition, and everyone was safe. The concrete frame was still sound, but it really upset the building occupants. All right, and in looking at this building, we've got a nice little missing section of mechanical, or of our ductwork here. And obviously it's been cleaned up, but I don't think anybody would want to be underneath that when it comes down. So looking at plumbing, there were significant water leaks all over the valley. We talked about untested systems as far as emergency response. Well, our buildings have been untested as well. So we started to see various systems have problems in light of this moderate earthquake that we experienced. So here, I think this might be the UGS offices over here, where you see the overturned cabinets, and we've got a mechanical fixture that's fallen from a tall 2-story ceiling. So damage at schools. Schools were already closed to students due to COVID-19 concerns, but after the earthquake, nearly all the school districts closed to all staff until buildings could be evaluated. So there were some impacts to the COVID-19 response. Hospitals luckily were fully operational with no injuries, and the University of Utah even initiated its emergency command center. And but some of the smaller, older clinics did have to shut down until they could be evaluated. So as far as the coronavirus response in the state, there were some impacts. The hotline was shut down due to evacuation of the call center. And then the state public health office had to stop testing samples temporarily, but they were able to resume testing within 24 hours. So looking at disbursement, this is a map of historic structures by SHPO. And you can see there's a nice little group in downtown Magna, and then a whole bunch of buildings in Salt Lake City, if you're familiar with the area. So with a really amateur overlay, I took a shaking intensity map and placed it over the top of this SHPO map. So you can see as we start to look at the MMI intensity ratings, we're looking at damage to those historic structures that's occurring with moderate shaking. So if you can think about what Keith Koper said earlier, that our major earthquake could essentially have 90 times the energy released. We really do have a big high leap or a high hurdle to clear with what we've got in our building stock. So key points, many building owners chose to evacuate pending evaluation, even if they had minor damage. People were nervous, they were scared. We saw damage to vulnerable building types, namely URMs and modular homes. We had extensive non-structural damage in old and new buildings. And then one thing that was kind of tying into what Crystal and Trent were talking about, we didn't have any volunteer requests for the structural engineering community. So that was partially due to COVID-19 concerns as I understand it, but ultimately assessments by the structural engineering community were contracted with building owners and tenants, and they were paid services. So the current state, right now, public entities have evaluations and repairs underway. Some private owners do as well. But one thing that's important to note is that there really is no requirement to self-report in the state of Utah. And there's no triggers to force detailed evaluations, except in the most extreme cases. Ultimately, the building official or the authority having jurisdiction can condemn a dangerous building. But you know, as we can see, it can get a little bit difficult in a small earthquake like this. So I think that's everything that I had, and I apologize for messing up the pacing, but I'll turn it over to you, Barry.
Thanks, Jessica. I sure am glad we got you into the mix here, because this is a wonderful presentation. I appreciate it. So I hope you all enjoyed this. It was a labor of love for us here. We like putting the information in one space that can show you from soup to nuts what happens here. So we're going to close out now with a couple of announcements, if we can change screens. So full screen, that's me. You want me to do this? I can't do it. You got to do it. Sorry, I'm mumbling. I'll go ahead and start. There is an upcoming ERI webinar planned by the Young Members Committee. It will be hosting this on August 10th. It's Advances in Seismic Risk Assessment Using Simulated Earthquake Ground Motions. If you have interest in attending this webinar, registration information is included in this, will be included in a follow-up email to you. And then lastly, we will be issuing PDF credits. You can learn more about learning from earthquake programs on the website learningfromearthquakes.org. PDH information will be provided in a follow-up email. We'd like you to complete the webinar survey to provide your feedback so that we can make these webinars even more impactful. You can learn more about ERI at eeri.org. If you're not already a member, you should consider it, and please see the follow-up email for more information about how to join. To find out more about upcoming ERI webinars, please check the ERI Pulse. And finally, we want to thank FEMA for supporting this webinar. And with that, I will thank you all for participating and hope you have a great day. Goodbye.